Hi, can you hear me? Great. So thanks, Avery, and I'd like to thank all the organizers for inviting me to tell you about this work. This is all joint with my colleague at Waterloo, Matt Satriano. Um, and so I'm going to be telling you about some spaces that don't normally show up in Schubert calculus. So I want to sort of make the claim that Schubert calculus is not just the study of flag varieties, that Schubert calculus is a way of life. It's a perspective that we can bring to bear on all sorts of objects in the world. And so I'm going to talk about quasi-symmetric things. So Vasu told us a little bit 2 days ago, I guess, about quasi-symmetric polynomials. And so I want to show you sort of how to situate this with respect to that. So the symmetric function ring shows up in sort of two main places, I would say, in Schubert calculus. There's this one story where you see sim, and it's essentially it's telling you the cohomology of a Grassmannian. Okay, and there's this other story that we talked a lot about during the summer school, which is to take the ring of polynomials and take a quotient by symmetric things. Okay, and this was supposed to look like the cohomology of your flag variety. Yeah, but I'm giving this talk, Frank. It's going to be okay. So what's going on in Vasu's talk, right, is he's taking this object. Oop, that pen doesn't work. He's taking this object here, and he's replacing it with quasi-symmetric things. This was Vasu. And he told us sort of how to think about this analogous coinvariant ring. Some beautiful combinatorics that came out of that. And I want to tell you what's going on sort of on this other side. I'm going to replace this sim here with a Q sim. And I want to tell you how this is really thinking about cohomology of something. Okay. And the something is going to be probably spaces that you may not have thought about at all, or maybe not have thought about very much. But I want to make the claim that they're, in many ways, like the sort of things that we think about in Schubert calculus, and you can do analogous Schubert calculus things with them, and there should be a rich source of a lot of attractive new mathematics along these lines. Okay, where is my clicker? Here's my clicker. Okay. So here's how we're going to build some spaces. So we're going to go raid the homotopy theorists for some things to study. So we're going to start with some space X. And X is basically going to be a flag variety, because we love flag varieties. But in fact, if you have a different space, basically anything will work here. Okay, so you have some space. I do need my space to have a special point. That's okay if my space is a flag variety, right? Because Frank told us that flag varieties are all quotients of groups. And groups always come with a special point. It's called the identity element. So I always get a special point in my space. And there's a few things the homotopy theorists like to do with spaces. The one thing is this notion of suspension. So I'm going to do this. The equation is hard to read. So I'm going to do the definition of suspension by mime. So let me take X to be a circle. So I have the circle. First thing I'm going to do with my circle is I stretch it up into a cylinder. Now I've got this tin can with the ends cut off. Okay? And now I take the top and the bottom of my tin can, and I squish them together. All right, so I don't know how my mime is. What have I got? I've got a sphere, right? Okay, and now actually I cheated a little bit. I have my special point, so I have sort of this stripe along the side of my can, and I'm supposed to squash all the copies of that special point together. But actually I still just have a sphere. Nothing actually happened when I do that. So that's what suspension does. It takes my circle, turns it into a sphere. And it does basically the same thing more generally. If I have a 2-dimensional sphere and I do this again, I'm going to get a 3-dimensional sphere. If I take a 7-dimensional sphere, I'm going to get an 8-dimensional sphere. Okay, so homotopy theorists love their spheres, so they love suspension. You do this thing. Okay, the other construction we want to do should be, yeah. Yeah. Yeah, basically. Well, it will actually make a difference if your space is bad enough. Yeah, it won't make any difference provided your space has some set of adjectives that I won't state. You get into trouble if you try to do like the Hawaiian earring or something. So I want to talk about loop spaces. So loop spaces are familiar if you thought about the fundamental group. I'm going to look at basically all the ways of putting a circle inside my space. So the points of my new space are going to correspond to ways of embedding circles in the first space. And it's supposed to be, again, it's a pointed thing. So there's a base point on my circle, and the base point of my circle should sit at the base point of my space. So I'm looking at ways of like drawing loops from a particular point. Okay. This is a very large space. Right? If you think about the number of degrees of freedom and how you can wiggle a loop, it's going to be a lot. Right? These are going to tend to be infinite dimensional. They may become disconnected. Right? In fact, there's going to be a bijection between the connected components of the space and elements of the fundamental group. That's basically what the fundamental group is telling you, is can you get from one connected component of the space to the other. So the space is extremely large. But actually, it's very nice in terms of the homotopy. So we have this nice relation here, which says that to map out of a suspension is essentially the same thing. Right? There's a correspondence between ways of mapping out of a suspension and ways of mapping into a loop space. So for example, if I want to map a two-sphere into my space, I can think of that as mapping just the circle into the loop space. For every point in the circle, I'm producing a loop. Okay, and this is something you can meditate on if you haven't done it before. There's some nice visualization exercises you can do to see why this is true. Okay. Well, this means, so what is homotopy theory? Homotopy theory is the study of how you put spheres of various dimensions inside your space. And this is saying that instead of putting some large dimensional sphere, I can instead take a smaller dimensional sphere and map instead into the loop space. So what this does on the homotopy groups is it just shifts them all by one. It's just re-indexing. So this giant sort of operation we did to make our space gigantic is sort of the topologist's version of re-indexing a sequence, which is something we want to be able to do. So it's somehow like a very natural thing to do, maybe not geometrically, but at least algebraically. Okay, but the problem is you can't understand this. Oh, right, so I have these two operations, so they're a pair of adjoint functors. I'm supposed to look at doing one after the other. That should be a thing you sort of always want to do when you're in this situation. And it should be, well, they sort of invert each other. So it's sort of an exercise in doing nothing, but it's the kind of doing nothing where your space gets a lot bigger and is not the same space anymore. Okay, but it should be somehow related to the space you started with. It should be somehow a fairly mild operation. Problem is it's very big, and it's very hard to visualize what on earth that looks like. And this is hard even not for us, but hard for the people who work in this business. And so they like to develop models of difficult spaces that are easier to understand and honestly just more combinatorial. Okay. So they only care about things up to homotopy. So you can always replace your space by something homotopy equivalent. And so Johann James, quite a while ago, figured out how to do this for these loop suspensions. He's going to show you the space, and I'm going to explain the space to you, and I claim you can really understand what this one looks like. And it's good enough for all the purposes that they need. And it's much more combinatorial. Okay, so here's how you build this space. So the points of the James reduced product, which is what it's called, are essentially sequences of points in your original space. Now, if I just had sequences of points, this would give me a disconnected space. There'd be no way to get between a word of length 5, a list of 5 points, and a word of length 6. But I have my special point. And the rule is that I can throw in and remove my special point from a list however I want, whenever I want to do that. So this means that if I have a word of length 6, and one of the letters of that word is a point that's very close to the base, then I can deform that towards the base and then drop it out, and it can become a point of a word of length 5. Okay, so this lets me move between things of different lengths. Okay. So it's a large space. It's still infinite dimensional, but actually it has this nice filtration. So words don't have a fixed length. If I have a word of length 7, I can always make it arbitrarily longer by adding as many base points as I want to it. But every word has a sort of minimum length that you get by throwing away the base points. And so that's giving me this nice filtration by these finite dimensional JNs. And there's nothing very exciting happening in the limit. So if we understand all these finite dimensional JNs, that's basically the whole story. And okay, we could have done this with almost any space, but if we have nice structure on the space that we plug in, we're going to get nice structure out again. So if my space is a CW complex, for example, if it's a flag varieties come with a decomposition into cells called Schubert cells. It's a very nice stratification. And okay, I need this other condition. I would like my base point to be one of the zero-dimensional cells, but that's fine for our Schubert decomposition. Right? The base point of the Schubert decomposition always is, I guess, the unique zero-dimensional cell there. So then when I do this, I'm going to get a cell structure on my James reduced product. What are the labels of my cells? Well, they're just lists of the cells that I started with the rule that I can add and remove copies of the special zero-dimensional cell for free. Okay, so the combinatorics of how I built my original space lifts the combinatorics of this larger space. Yeah. Yeah, it's an in scheme. I'm going to tell you how this is an in scheme. Yeah. Yeah, so at first I didn't think this was going to be an in scheme because we knew it couldn't be normal. And then we thought maybe it just didn't work at all. But it's fine, it's an in scheme, and I'll show you the equations. Okay, so but first we can do something easier. Right? We can stay in the world of algebraic topology and still get something interesting. So I said before that what are the cells of this thing like? If I have an indexing set for the cells in my base space, I want to look at lists of those cell labels, or I can add and remove for free copies of the special label on my special point. And in the case where all of my cells are even dimensional, that's a very restrictive condition, but actually is fine if I'm plugging in a complex flag variety. Okay, lots of things where this is true. Right? In my Schubert stratification, all of my Schubert cells look like some power of a complex affine space. So they're all even real dimensional. If I'm in this setting, then it's quite immediate by the cellular cohomology construction that what my cohomology ring is going to look like, well, it's just going to be, I'm going to get one cell, one cohomology class for every cell, and I'm going to get one cell for every one of these lists. Okay, so you can write down immediately what this ring is going to look like, provided you know what the ring looked like to begin with. And so the one case that I'll sort of focus on today, because it's more concrete and we'll get sort of combinatorics we've seen before out of it, is just to take projective space. I'm going to take infinite projective space just to avoid some kind of boundary conditions and instead have to fuss about limits. But I'm going to be lazy and not be careful about the limits. Yeah. No, I get cohomology. Everything's fine. Take the cellular cochain complex. Just functions on cells. Yeah, but you can work on these finite pieces. I'm taking limits, but I'm not being explicit about all my limits. Yeah. No. Yeah. Yeah, but I'm gonna be very sloppy today about limits. There's a lot of limits to take, and I'm not gonna do them. But you can look in the actual papers for like the precise statements. There are some tricky technicalities that I'm gonna try to hide. Yeah, Alan. Yeah. In fact, if I don't start with a group, I'm gonna get a ring structure because these spaces always have a product because they're loop spaces. I think you can't probably have two of them simultaneously. Yeah. But James Reduced product has a product under concatenation, which comes from the concatenation of loops structure. So these are always H spaces. You're going to get these like pair of dual Hopf algebras off of it. Yeah. But we haven't made any use of that extra structure. I'm not sure quite what to do with it. Yeah, it does. It does. Well, no, it gives you. Yeah, okay, but I mean, it's more naturally giving you ensim, but sure. Okay, so I'm plugging in here projective space. Now my cells are just labeled by dimensions, or complex dimensions, right? So they're basically just numbers, and so the indexing set for the cells here is just what I would call compositions in an introductory combinatorics class. And okay, what ring have we seen that has a basis labeled by compositions? Well, Vasu told us one a couple days ago, which was QSIM, and that turns out to be the right answer. So there's actually an isomorphism between this cohomology ring and this ring of quasisymmetric functions. And you can check this. In fact, not that hard. So this was observed by Andrew Baker and Birgit Richter maybe 15 years ago, but they're actually coming from this homotopy theory world. They're not Schubert calculus people. They haven't been trained by Alan to not be pleased just to notice you have a ring, but to actually want a ring with a basis, right? To notice when your ring appears with a canonical basis, and to make use of that structure. So, okay, under this isomorphism, we should be saying, well, over here, I had this canonical cell decomposition. Canonical provided you assume that there's like a best way to put a cell structure on CP infinity. And there's like a standard way to put that cell structure down. That gives me sort of a standard cell structure here, which gives me a standard cellular basis of this cohomology ring. And now I have this isomorphism to QSIM. I ought to be asking myself, where does this basis go? What does this basis correspond to? Like, what is the topologically corresponding basis over here? Okay, when we did this with the Schubert cell decomposition and this isomorphism to symmetric functions, this is where we found our Schur functions. And Schur functions are a very beautiful thing that we want to understand. So this should be some kind of analog of that. And okay, they could have done this. It wasn't that much extra to do. You're going to get an explicit basis, going to be maybe the most classical of all the bases of quasi-symmetric functions. It's the monomial basis. Okay, so I'm going to tell you a little bit more about that. So here's how quasi-symmetric functions work, whirlwind tour. So given a composition, I'm going to define this quasi-symmetric function here. It's going to be the sum of all the monomials whose exponent vector, if you ignore zeros in the exponent vector should look like alpha in the correct order. So there's my monomial quasi-symmetric function. That's what I'm claiming represents my cohomology classes. And I'll just define QSIM to be the span of all those things inside polynomials, or power series, I guess. Okay, so what we want to do with Schur functions, we want to multiply them. There was a Littlewood-Richardson rule. There's also a rule for multiplying these monomial quasi-symmetric functions. And it's actually quite interesting. It's in terms of shuffling words together in various ways. So people tend to think that monomial bases have to be boring, but there's actually a significant amount of structure into how they work. There's something going on there. And so this says that actually you understand the ring structure of this space, as well as you understand like the cohomology ring of a Grassmannian. Right? You have this explicit basis, and you have this explicit multiplication rule for how to expand in the basis multiply basis elements and expand again in that basis. And there's a sort of meta theorem that goes with this, which says anytime you take x, x doesn't have to be projective space. If you take an x that you understand to some degree, and you apply this operation to it, you will get a new space that you understand essentially to the same degree. So if I plug in, say, a Grassmannian, where I understand the cohomology very well, I have a Littlewood-Richardson rule that will lift to a similar understanding here. I'm going to have classes labeled by sequences of partitions, and I'm going to have a rule that lifts the Littlewood-Richardson rule for multiplying them together. And if you plug in a thing you understand sort of, like the full flag variety, you're going to get a thing where you understand sort of. Okay, so you're going to have like, we had Frank telling us about this Pierre rule on full flags. It's going to lift to a sort of way of multiplying some of the classes here, but not all of them. Okay. You have Schubert polynomials representing things here. You're going to be able to lift those to some kind of generalization of a Schubert polynomial over here that you can do explicit multiplications with. So cohomologically, I claim that this sort of does approximately everything you would want to do. Every time you understand some space, you get to plug it into J, and you get another space that you understand as well, but no better. But of course, we don't want to be happy only thinking about ordinary cohomology. Right? We spent a lot of time over the past week or so thinking about how we enrich the cohomology ring by going to K-theory, adding equivariance, looking at quantum things. And we want to be able to do that here. And so I want to tell you sort of how you can lift some of these stories as well in less generality. Right? I won't be able to talk about all spaces in this way. It's going to be a little harder. Yeah. Xi is you should think of it like the divisor class on P1. Yeah, so I'm cheating a little bit, right? But yeah, okay, you should think of it as like, there's various ways of fixing the technicalities. Yeah. But it is the one-dimensional class. It corresponds. Depends how you want to think about it, right? But I would want to think about it basically as the divisor class. What's that? No, they don't individually live there. Right? The only things that live there are quasisymmetric. Yeah, but there's a map from a product of projective spaces onto this thing, and they're living there. Yeah. Yep. Good question. I'm not sure. Yeah, I don't know. It's certainly a very special space, but I haven't checked how much that tracks the same universal properties as QSUM. I haven't thought very much about the Hopf algebra structure in particular, which you would want to do. Okay, so in order to go to other kinds of cohomology theory, it's helpful to move from algebraic topology land into algebraic geometry. And so we're going to do this thing where we build these as limits of schemes. Okay, so I'm going to take a ring, and you can take any ring you want, but let's just imagine maybe one variable polynomial ring. And I'm going to take a maximal ideal. Probably doesn't even need to be maximal. I'm going to have an ideal, but let's take this one. And I'm going to look at a tensor product of a bunch of copies of this ring. And here's my notation for like sticking something in the kth copy of this tensor product. Okay, so I'm going to build a subring of this, where what I've got is I take essentially lists of elements of my maximal ideal, and I'm allowed to slide them back left and right among these various tensor factors. So this will make more sense if you spent more time thinking about quasi-symmetric functions, and less sense if you spent less time thinking about this. But the thing we can understand, maybe, is if you do this in the case of polynomials in one variable, and the homogeneous maximal ideal generated by that variable, this is exactly going to return the ring of quasi-symmetric functions in n variables. But you can do this more generally. You can do this with any ring. And so the claim is that if you start with a space that has algebraic structure and you apply the James reduced product, you're going to get another space that it lives in the same kind of world. So if I start with an affine variety, I'm going to get an affine variety out. If I start with a projective variety, I'm going to get projective variety out. If I start with something quasi-projective, I get something quasi-projective, whatever you want. So I'm not going to write down all the equations. I'll just tell you the affine version because it's a little bit easier. So I start with my affine variety. There's some, I have the coordinate ring. My points, the points of this space are corresponding to the maximal ideal. So I have my special point, and I have my special maximal ideal. And I can do the construction that I had on the previous slide, and I get some sort of strange subring, but I can just hit it with spec, and that's giving me the nth truncation of my space. And you can do the same thing projectively, but I won't write it down because it's a little ugly. Okay, so I get these spaces, and they're not that bad. They're not normal. They're basically never normal, but the normalizations are very nice. The normalization map is exactly just coming from taking this product Cartesian power of the space you started with. So if I'm starting with flag varieties, I'm just popping out other flag varieties right here that I can understand very well. Yeah. Fit what together? Oh. Good question. Didn't try that. Yeah. For the most part, it's not going to make any difference what point you take, but of course, you know, there might, yeah, sure, there might be interesting structure there. Yeah, it's a functor. Should be okay. Well, I'll show you one example on the next slide that you will see very easily is not normal. And the structure basically propagates. So, yeah. Yeah, that's exactly what's happening. This construction involves also like folding, essentially, right? And it's sort of weird. So let me show you the one example. Here's one example that I can actually understand. It's the only one I can visualize, and okay, I got a lot of value out of staring at this one example for a while. So the only one that's small enough to really see is to take the affine line and take J2. Now I'm going to get some kind of surface here. And so that's supposed to be exactly looking at quasi-symmetric functions in two variables. So I need to write down generators for the ring of quasi-symmetric functions in two variables. The obvious things to write down are x, y, and x plus y. Those are going to generate symmetric functions. And it turns out it's enough if you throw in this quasi-symmetric thing, x squared y, that generates everybody. So I just need these three generators. And that's hard to think about. I don't normally like to present my coordinate rings as subrings. I want to like write them as quotients of polynomial rings. It's easier to think about. So I'm going to substitute in these three variables in for these three polynomials and think about what relations they satisfy. And it turns out they satisfy just this one relation. So I'm getting just this actual surface in 3 space. And so I can't draw that very well, but I draw, so these are going to be slices in values of t. And we'll see. I tried to learn in Beamer how to do an animation, so I'll try to actually make this thing go. We'll see if it works. Yeah. Okay. So these are slices through various values of t. On this surface, you can see that right here, right at t equals 0, you're seeing this little cusp, and otherwise you're seeing this node, and this loop is getting bigger and bigger, and as t goes to infinity, it starts becoming reducible and coming apart into a couple pieces. Yeah. So I mean, you can see this non-normality, right? It's happening right there. Yeah. Yeah, exactly. And this comes from, what am I doing? I'm taking 2 copies of A1, and I'm gluing them along, I'm like gluing all the axes together. And that's folding everything like this. Okay, I'll leave the picture up for another 10 seconds or something. So you can. Yeah. Yeah. Yeah, I don't actually know how to present this ring in general, but that sounds like a thing that maybe someone's done at some point. That sounds like a thing someone would have done at some point. I couldn't find them easily. It seems like a thing that someone should do. It would certainly make these calculations a lot easier if you had such a thing. It took me. I agree. It should be very interesting. Yeah. So I think like here's a bunch of schemes. They look interesting. I've done very little with them, and all you young, energetic people, everyone gets a scheme. Okay, so okay, now I'm going to go to equivariant cohomology and tell you how the story lifts there. So I think people have wondered for a long time, right? We love symmetric function theory, and every time we do symmetric function things, we like to write down double analogs and work out the analogous combinatorics. And there's this vast literature on quasi-symmetric polynomials, working combinatorially, working representation theoretically, and no one really knew the right way to put y's in. But you can kind of guess various ways to insert the letter y, and you probably guessed this one, actually. But now I'm telling you this was the right guess. Okay, this is the right thing to do, because it's going to match up very nicely with the equivariant cohomology of this space. So this formula is kind of hard to parse, but basically what's going on is every time that I saw a variable to a power, I'm doing something like polarization. So if I saw like x3 cubed, this is going to become x3 minus y1 times x3 minus y2 times x3 minus y3. I'm splitting that power apart in what's probably the obvious way if you've thought about a lot of double polynomials. And then I'm going to define this sort of double quasi-symmetric function ring to be the span of these, just like before. Okay. And the theorem is this is the right thing to do because the ring that I'm getting here is isomorphic to the equivariant cohomology ring. So there's a torus, right? There's a torus acting on CP infinity. And that's just going to act diagonally on all these copies of CP infinity. And that's acting then on the James reduced product. Yeah, I think that's overkill. But yeah, I mean, that's true. Yeah, you can write this down very explicitly. Okay. At least, in the case that you're using projective space, if you try to plug in something more interesting, you're going to have to work a little harder to do something like this. Okay. So the cells that we wrote down before, right? This torus action, they're all T invariant. So they're all giving me equivariant classes. And so I have these equivariant classes, and they're supposed to correspond to some particular elements of this double quasi-symmetric polynomial ring over there, and it's these, okay? Yeah. Yeah. There's a lot of movement between the space and the normalization and looking at finite truncations, and there's yeah, you're right, but there's a lot of moving back and forth between these various perspectives to avoid various issues that you're thinking about. Okay, and it gets worse in K-theory. Okay, we have to be even more, there's more things to worry about. Okay, so that I think is what I'm gonna say about, oh no, great. So I wanna say one more thing about equivariance. So you also get a nice product rule. So I want to do the thing that I do in the cohomology of Grassmannian. I have two classes. I want to multiply them together and expand in that basis. And you can do this in the equivariant cohomology of this James reduced product. I want to multiply this class times that class, and I get this class. This is basically just lifting your favorite way of computing in the equivariant cohomology of the thing you plugged in. So in this case, projective space. Okay, so there's lots of ways to compute equivariant cohomology of projective space. Probably that was homework at some point this week. And you take sort of any version of this, and you can soup it up into combinatorics for the James reduced product. So here I took one particular way, which can be you're going to count some kind of funny looking diagrams like this, and you're going to count them not just by counting, but you're going to assign these gram positive weights to each one of them and add them up, and those are going to be your structure coefficients. And you can do something like this more generally, right, if you plug in something here where you understand equivariant cohomology. Okay. So I don't know. I mean, this is sort of combinatorics I haven't exactly seen before. Okay, so now I want to turn to K-theory. K-theory situation is a lot harder. I can definitely only tell you about the projective space case. I have no idea what to do essentially anywhere else. But in that case, I can tell you a nice story. So I'm going to define what are going to be my polynomial representatives, and I'll call them quasi-symmetric monomial glides because they sort of feel like they're built out of the slide and glide technology that Sammy and Dominic developed at some point. So the way this works is I'm going to take my word alpha, and I'm going to stick a bunch of zeros on the front of it. And then I'm going to start sliding numbers to the left. And there's two rules. So the one rule is if I see a 0 followed by a number, I can either slide the number to the left, or I can slide the number to the left, but also leave the number behind. And when I leave a number behind, it turns red because it's so embarrassed. Okay, and that's important. I need to keep track of that extra information. Okay, so I do this, and I do this in all possible ways, and I see all the words that I can get to. And the words end up being colored. Right? Some of the letters are just in black, and some of the letters are in red. And I don't care about how I got to the word. If I got to the word in two different ways, it's just one thing. But I do care about distinguishing things that are red from things that are black. So I can, in fact, get the same uncolored word, but colored in different ways. Those count separately. Yeah, Tianyi? Let's say they can't move. But you can, there's some choices in how you define this algorithm that will give you something equivalent. So if you would like the red letters to move, you can make that happen in a good way. But they never need to move. Okay, so these are these polynomials I want to write down. Okay, does the definition make sense? Okay. So now I'm going to write down this generating function for these things. And so over here, I'm just writing down this monomial. This is ignoring the colors. It's just looking in every position of my word and saying what number is there, not what color it is, and let me take that appropriate power of that variable. And the colors are just going to show up to give me this sort of silly sign out front. I'm just going to keep track of the parity of the number of things that got colored. I write down these polynomials, and I claim that these represent K-theory classes on this space. So, okay, now I haven't even defined this notation, but this is, so quasi-symmetric functions, they're power series, but they should be actually in bounded degree. Okay, and now in K-theory, I should be not insisting that things have bounded degree. They're actual power series. Yeah? No, I don't have a variable x0. They're indexed by the positions. So I'm one indexing the positions of my string. And the values here become the exponents. Yeah, thanks. If I just do the first moves, I'm getting the ordinary things. Yeah, the K-theory structure is coming from leaving stuff behind and turning it red. Okay, and so this -1 is keeping track of sort of how K-theoretic you are. So the tricky thing here is that when you have a space with a cell decomposition, you get not just to know what your cohomology ring looks like, you actually get a basis. When you do this in K-theory, you know that you can write down the additive structure of your K-theory ring by looking at these cells. You know that the rank of your K-theory ring is going to be given by counting cells, but you don't actually get the split stuff. You don't actually produce a basis in K-theory. And the way we've been getting around this all week, because we're in Schubert land, is that we take structure sheaves of Schubert varieties, or ideal sheaves of Schubert varieties. And here that's not going to work for us very well. So we have to work a lot harder to produce some kind of canonically defined class in K-theory to give us these basis elements. But I claim there is a way to do this, and I'll sort of sketch a little bit how that goes. And I claim that when you do it this way, which is the only way I know how to do things, what's going to pop out are exactly the polynomials that I wrote on the top of the screen. Yeah. 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 That's right. We're not smooth. So, okay. So the first problem, when I first started doing this, I didn't realize I had schemes at all. And so this was bad. But now I have schemes, but they're still not smooth. So I'm stuck in K-homology. But somehow we can cheat and produce these things. Okay, so let me show you okay, so this is like somehow like half of the work that goes onto this paper squished onto one slide, 2 papers, but all squished onto one slide. What we want to do, we want to just like take the class of the structure sheaf, and that's not going to live where we want it to live. So what we do instead is we say, well, this space actually has this very nice normalization. The normalization is just this power of a flag variety. It's just a product of a bunch of copies of CP infinity. And so over there, I have structure sheaf classes, or at least I should be looking at finite truncations. I have these nice structure sheaf classes, and everything makes sense over there. And now you need to take these classes and try to push them forward into. Is that okay? Can you hear me now? Okay. And try to push them forward again. And the problem is you have sort of no idea where anything goes or what the image is supposed to be. And for this, we end up using these theorems of Briand and these Knudsen ideas of way of looking at multiplicity-free subvarieties of flag varieties. But this normalization is a flag variety. It's a product of projective spaces. And so you get to use this to say, so I take this thing and I pull it back, and I get something that's not a Schubert class anymore, but it turns out to be multiplicity-free in the Schubert basis of this product of projective spaces. And so that tells me how to write down its K class in terms of the Schubert structure sheaf basis of that product of projective spaces. And I get some answer in terms of Mobius inversion on a poset. And my posets are kind of terrible. They look like this. Okay, so yeah, but it's not graded is the problem. So on the bottom, I have all the things that was shown up in the cohomology calculation, all the ways of sliding things and never turning anybody red. And above that, I have sort of all the things you can get by gluing those together in various ways. I've got this poset, and I need to understand Mobius inversion on this poset. And you can do this, and after a couple of big sign reversing involutions, you learn that the coefficients of the Mobius function, the values of the Mobius function, exactly coincide with these counts of things you can slide to, how many ways things could have been colored. Get this. So the combinatorics ends up matching this Mobius inversion count, and then you win. So then you actually get to know that these things live in the right place and that they're a basis and that there's the right number of them. Okay, so we were not the first people to try to write down K-theoretic analogs of these monomial quasisymmetric functions. There's a remark in a paper from a while ago of Thomas Lamb and Pasha Piliavsky where they guess combinatorially at a K-theoretic deformation of monomial quasisymmetric functions. And they're not the same as what we've got, but they're almost the same. Their things, they don't write them this way, but one way to think about what they've got is the same sort of sliding rule, like this, except that this rule is the same, and I start from the same place. But the second rule, instead of leaving behind a red k, they would want me to leave behind a red 1. And if you use that instead, you get this other class of polynomials that do not represent these K-theory classes I wrote down. But somehow the combinatorics is very, very close to being the same thing. And I think I timed this perfectly. So thank you very much.